everyone. So we are kicking off Unit 3 with some more rules for taking derivatives, and this one is a big one. This one gets used quite a bit. This is called the chain rule, and the chain rule is not about a specific type of function. It's more like the product rule or the quotient rule. It's something that you're going to use to combine functions, except this time we're combining functions with composition, meaning we're putting one function inside of another. Okay, and this actually shows up more often than you think it would. You'll see some examples as we go further on down the page. But when you have a function inside a function, the way the chain rule works is we start with the function on the inside, and we take the derivative of that, okay? And then you work your way toward the outside, and you take the derivative of that outside function, but when you do that, you leave the inside function alone. And I think that will make more sense once you see the first example when I say leave the inside function alone. But you're doing a derivative of the outside function in terms of the inside function. So let me show you how this works here. We're going to do this first one in two different ways. We're going to do it using the chain rule, and then we're going to use it kind of the old-fashioned like simplifying rule, and we'll see that the answers come out the same. Okay, because this is one we could do either way. Now, there's a lot of functions where you don't really have a choice. You have to use the chain rule, but I'm just doing this so you can kind of verify that this does, in fact, work like you think it should. So, with this one, my inside function is here, the 3x squared plus 1. That's my inner function. Okay, so as far as my derivative goes, I'm going to start with the derivative of 3x squared plus 1. So 3x squared, that'd be 6x. And then the plus 1, because I'm doing a derivative, doesn't really matter, right? And then I'm kind of moving to the outside function, which is really like something squared, okay? So the square is my outside function. And when I do the derivative of something that's being squared, I always bring the 2 down in front, and then this becomes a power of 1. So this is going to be 2 times, and then instead of just an x, we have 3x squared plus 1. That's what I mean when I say leave the inside function alone. And technically this would be to the power of 1. We don't really need that power of 1 there, but that's the idea, is that the derivative of this thing is 2 times whatever happens to be in the box, and in this case the box is 3x squared plus 1. Now, you could get away with leaving your answer here, okay? I'm going to simplify it just because I want you to be able to compare it with the next problem. So 6x times 2 is 12x. And then I'm going to distribute that to the 3x squared plus 1. So my derivative is 36x cubed plus 12x. Okay. And just to prove to you that what I just did worked, I'm going to take this function and FOIL it out. I'm going to expand it. Okay, so let's see, 3x squared plus 1 times 3x squared plus 1. That's going to give me a 9x to the 4th. It's going to give me a 3x squared and a 3x squared, which is a 6x squared. And then a 1. And so now when I go find the derivative of that, 9x to the 4th, that would give me a 36x cubed. 6x squared would give me a 12x. And the plus 1 goes away when we take a derivative. And so that's what we have. And so what I want you to notice is that these answers came out the same. And so I'm not going to do a true proof of the chain rule for you, but I just want you to be able to verify that, like, look, this does indeed get me to the right answer. Okay, so let's take a look at this example 2, well, I guess, and example 3 here. In example 2, again, I would always start by identifying kind of the inside function. The inside function is 3x minus 1, and that is inside a natural log function. Okay, so for my derivative, I'm going to start with the 3x minus 1. Derivative of 3x minus 1 would just be 3. And then derivative of natural log, we would typically say is 1 over x, but it's really 1 over whatever it is you're taking the natural log of. So if my inside function is natural log of something, and I go to take the derivative would be 1 over whatever that something is. So this is going to be 1 over 3x minus 1. So instead of x, I'm putting my 3x minus 1 in place of that. And then I would probably just go ahead and do the 3 times 1 and make this 3 over 3x minus 1. Because then the next part of this is to find f prime of 2. So to find f prime of 2, then I want to plug 2 into this thing. And so I'm going to go 3 over 3 times 2 minus 1. That's 6 minus 1, which is 5. So this answer would be 3/5. Okay, example 3. Example 3 is a triple chain rule. Okay, we have a function. We have this 2t hiding inside a sine function. I guess really it's in this whole thing. 5 minus sine of 2t. The 5 is not going to end up mattering too much. And then all of that is inside the tangent function. Okay, so that's the order I'm going to take my derivatives in. So I would start out with derivative of 2t, which is 2. That green might be hard to see. Sorry about that. Then I'm going to go do the 5 minus sine of 2t. Well, the 5 really disappears. Okay, because when I say disappear, it's because the derivative is 0. Derivative of negative sine. Well, derivative of sine would be cosine, and then I'm going to keep that negative 1 with it. That's the constant multiple rule. So this is 2 times negative cosine, but I'm leaving that part that's in green alone. So negative cosine of 2t times, and then on that very outside I have tangent. So my derivative of tangent is secant squared of the whole thing that was in there before, so the 5 minus sine of 2t. There's really not a whole lot of simplifying I could do with this one. I could probably, like if I were to rewrite this, I would probably just put this negative sign on the 2 and make it a negative 2. That's usually better than writing it this way because sometimes that can get mistaken for like a subtraction. But other than that, there's not much else we can do with this. That thing is just the derivative. Okay, let's try a couple more. Slope of the line tangent to the curve of y equals sine to the power 5 of x. Okay, so slope of a tangent line, that is once again a derivative, right? I do want to point out before we start here that this thing, this y equals sine to the 5th of x, that is a shorthand way of writing sine of x to the power of 5. And it's important that you know that that's really what that's saying, because you have to be able to tell what's on the inside and what's on the outside. The inside function is the sine of x, and the outside function is the power of 5. Okay? So when I go to do my derivative, derivative of sine is cosine times, and then when I have something to the power of 5, and I'm just going to kind of sketch this up here, something to the power of 5, and I'm taking a derivative. By the way, when I draw this arrow, I'm saying I'm taking a derivative. That's a little sloppy notation-wise, but that's always going to be 5 times the something to the 4th power, right? If that was an x, it would be 5x to the 4th. But in our case, it is going to be 5 times sine of x to the 4th power. And that's really it. That's my derivative. I could take this and write it as sine to the 4th of x, but I know that I'm about to plug in a pi over 3, and so I think writing it this way is going to make more sense for that piece. So now I want to know what is the derivative specifically at pi over 3. So let's do cosine of pi over 3 times 5 sine of pi over 3 to the power of 4. Now, if this were a free response question, you could get away with leaving your answer right there. Once you plug your numbers in, once your values are all numerical, you'd be good to go. I am going to go ahead and evaluate this because I do worry that this could show up on a multiple choice question and you would have to know how to evaluate it down to a single answer. So we need to kind of revisit some trig to figure out what sine and cosine of pi over 3 are. I'm just going to kind of sketch up here for you. This is the first quadrant of your unit circle. Pi over 3 is this top coordinate, okay? And the coordinates at that point are 1/2, comma, square root of 3 over 2. So remember, this is the cosine and this is the sine. So I'm going to plug those numbers in. So cosine is 1/2 times 5 times sine of pi over 3 is square root of 3 over 2, and we're going to raise that to the 4th power. I'm kind of running on the assumption that we're doing this without a calculator here, okay? So let's do some math magic here. 1/2 would be 1 over 2. I'm going to take the 5 and write it as 5 over 1 because I think that'll look more reasonable in this next step. And now let's talk about how to raise this thing to the power of 4. Just go slow here. Square root of 3 to the 4th power. Well, if I have 2 square roots of 3, that makes just a 3, right? Because that's squaring a square root. And so I'll end up with a 3 and then another 3, because if I have 4 square roots, I would get a 3 and a 3. So that's going to leave me with a 9. And then on the bottom, 2 to the 4th power is 16. And then I'm just going to multiply straight across. So 1 times 5 times 9 is 45. 2 times 1 times 16 is 32. And that right there is my final answer. That's my slope of my tangent line. Okay. Example 5 says, so show that the slope of every line tangent to the curve, whatever, is always positive. Okay. If we're talking about slope of tangent lines, we're talking derivatives, right? I would actually take this expression and rewrite it as 1 minus 2x to the power of negative 3, which I can get away with because there's nothing up there, nothing else up there on the top, so I don't have to worry about like something else being up there. There's just a 1. But I am going to have to do chain rule because I have this function inside of this power of negative 3 function. So let's do a derivative here. My inside function, 1 minus 2x, that has a slope of negative 2, or a derivative of negative 2, I should say. And then for my outer function, if I'm thinking about something to the power of negative 3, that derivative, I'm going to bring down the negative 3 times whatever's in that box, the parentheses, so 1 minus 2x. And then I'm going to subtract 1 from the exponent, so that's a power of negative 4. Now, in order to answer this question, I'm going to clean this thing up a little bit. I'm going to say y prime equals negative 2 times negative 3 makes a positive 6. And then I'm going to take this thing, and because it's a negative exponent, I'm going to put it on the bottom. So the question here is, and realistically, if this was like a short response question, I would be a lot wordier with this. But the question is, how do we know this is always positive? Okay. Well, if you look at the top of this thing, the 6 is always positive, right? Because it's constant, right? Because it is positive, and there's no variable up there. So always positive. I guess I should say no variable. On the bottom, we're raising something to the power of 4. So that's also always positive because it's an even power, right? If we raise something to an even power, it always has to come out positive because an even number of negatives would turn positive. So if this is always positive and this is always positive, then your derivative is always positive. Okay, that's kind of the point they're driving at here. Okay, one last example here. Example 6, we're taking a derivative. All right, this one is a little bit tricky because we've got a product rule in here also. So this is telling me I'm going to have to use product rule. Actually, I'm going to erase that circle because that might confuse us. But here's our u and here's our v. Okay? And we need to think about u prime and we need to think about v prime. Well, u prime is just what's the derivative of x to the fifth? Well, that's 5x to the fourth. But v prime, we've got some chain rule going on here. So in our chain rule, we've got a 5x living inside a cosine function. Okay? So for my v prime, my derivative of 5x is 5. And then derivative of cosine is negative sine. And remember, when I do that, I leave the 5x alone. And I'm just for the sake of like cleaning this up and not confusing myself later, I'm going to rewrite this. I'm going to put the negative on the 5 and just make it a negative 5 sine of 5x. Okay, and then for quotient rule, I'm sorry, product rule, I'm doing u prime v plus v prime u. So that's going to look like u prime is 5x to the fourth. Oh, I should label this as a derivative, sorry. dy dx equals u prime, which is 5x to the fourth, times v, which is cosine of 5x, plus v prime, which is this thing, and then times u. I'm actually, because this is just a monomial, I'm going to put the u first. So I'm going to say x to the fifth times, okay, because this is negative, that's really going to make this whole second half of the expression negative. So that negative sign is going to come down here and turn this into a subtraction. And then I'm just going to make this a 5 sine of 5x. It would not be wrong if you left the negative over here on this term. Just usually if you've got negatives kind of mixed into the term somewhere, we usually just pull it out front and just say the whole term is negative. So I took the negative off that 5 and just used it to turn my addition into subtraction. But other than that, I'm just leaving my answer right there. Okay, that's my derivative. That was what the question was asking. I'm good. So that's it for chain rule. We've tried a few of these. You're going to see a whole bunch of these this year. There's a few examples in your homework I'd like you to try. And then I'm sure we'll be practicing with this over the next couple of weeks.